Okay, what can you tell me? What can you tell me? When is a function, let's start informally. What does it mean for a function to be increasing to increasing? Okay, as an ant, tell me, in terms of an ant, let's start in terms of an ant. As an ant, what? Okay, walks from left to right, so walks in the positive x direction, what?
It's gonna move in the y direction.
Going up. Okay, good. Yeah, so what does it mean to decrease then? Obviously, as an ant moves in the positive x direction, he goes down, right? Okay, so how could we say that mathematically then? So let's ignore calculus for a minute. Let's just say for an increasing function.
The slope.
Okay, but increases, those are words, how do we do this mathematically? So say we're gonna pick two values, like x1 and x2 or something.
M secant is greater
Say it again?
than, M secant is greater than 0.
Okay. How about, and can we even make it simpler? If we just have x1 and x2, can you tell me if, let's just say x2 is greater than x1. x2 is greater than
F of
x1.
x1 is less than f
There you
of
go.
x2.
So I gotta say, then f of x sub 2 would be greater than f of x sub 1. Which, if that's true, then the function is increasing from x sub 1 to x sub 2, right? Something like that maybe, right? If any two numbers, x sub 1 and x sub 2 in the interval where x sub 1 is less than x sub 2, that implies that f of x sub 1 is less than f of x sub 2. The y values would have to increase, right? And then vice versa for decreasing. Okay, what about when we want to calculusify this? If we want to add calculus to this, we can make it simpler. Increasing is where? Functions increasing in terms of calculus where?
Or M tangent.
Where, okay, so what's the calculus concept that's going to exactly hit this? What derivative? Yeah, because what's a derivative?
The rate of change.
Rate of change, so graphically it's a slope, right? A function's increasing where its slope is positive. There you go, right? So where the derivative is positive, the tangent to the curve, which is just giving us the slope of the curve, right, is positive. So we can say something like that, okay? If f prime of x is greater than 0 for all x in some interval, right, from a to b, then f is increasing on that interval. Okay? Now notice how there's some stuff going on here that's kind of, you could just easily gloss over and not catch. Remember that this is a closed interval, right? So if we want to, if the function is continuous on a closed interval and it's differentiable on the open interval, right? So we know that we can get smooth on the interval. Then we're saying that if the derivative is greater than 0 for all x in the open interval, right, then we know that f has to be increasing on the entire closed interval, all the way from a to b. So I could stick my pen on the board at x equals a and trace the function all the way up to x equals b, and it would be increasing the whole time, right? It's what you said, but we just have to make sure that we're all the fine print is there in terms of calculus, so there's no loopholes, right? Conversely, if the derivative is less than 0 for all values of x in this interval, then the function's decreasing on the interval, okay? What if f of x equals 0? What's that mean? Straight horizontal line, so it's neither increasing nor decreasing, right? And at any one place on the function where the tangent line is horizontal, is it increasing or decreasing? No, you're right. Not a trick question. It's not, right? If the tangent is horizontal, that is the boundary between increasing and decreasing. It's neither one of them, okay? All right, so let's take an example here. Let's do something similar. I can't remember if we use this exact function or not, but it doesn't make any difference. Let's take this function and let's build a table and see what we can see about the interesting features of this graph. Okay, we're going to add one more row to it this time. When we did our absolute extrema problems, we really only needed 2 rows in the table, but now we're going to add the 3rd row. And here's a general rule on the table. The further down the table you work, the more bang for your buck that you get. There's more information contained in the table as you move down the rows, from top to bottom. Okay, so let's make our table. First we gotta differentiate, don't we? We need to know what the derivative is. So what are we gonna get? What's the derivative of the first term? Second term?
3x.
Okay, good. So why don't we go ahead and find our critical numbers while we're at it? How about? Okay. So, maybe our critical numbers over here. So let's find, are there any critical numbers where that derivative is undefined? No, it's a polynomial, so we're fine there, right? How about if we set it equal to 0 and solve? How do I solve that? Good, factor out of 3x, leaving me with, so what are my critical numbers? Okay, 0 and 1, good. All right, so now let's go ahead and let's make our table. Say it again.
Like on all the other ones, it said where it's going from like negative
Ah, okay, yeah, good question. Doesn't give us a domain on this one. So what do we assume?
to
All reals, yeah. That if we don't specify a domain for a function, we're assuming the natural domain of that function, which is the biggest possible domain of the function, because we haven't implied any restrictions, right? So what is the domain going to be for this one?
Negative infinity.
Yeah, all reals, good. So we know that the domain here is negative infinity to infinity, right? So we need that when we build our table. Right? We build our table, our first row is x, and we're going to go all the way from, and I'll put open brackets there, right? Negative infinity, so that's telling me it goes all the way to the left, up to positive infinity on the right. Okay. Then I've got f and f prime. Okay, so now we're going to start to add some interesting things. So we had some critical numbers, right? The critical numbers were at 0 and 1. What's going on with those critical numbers in row 3? 0, right? Because we're just evaluating. Row 2 is the value of the function. Row 3 is the value of the derivative for these particular values of x, right? So if we go down to row 3, we know that the derivative has a 0 value at 0, and it has a value of value of 0 when x equals 1. Those are zeros of the first derivatives, and therefore we can identify those as critical numbers, right? Okay, while we're at it, let's just go ahead and add the values of f at those places. If I plug in 0, what do I get back? 0. Okay, do you see that this is really just an ordered pair, isn't it? Just tilted sideways. I guess I mentioned that yesterday. What's the value of the function at 1? Not 0. Negative 1/2. Okay, so those are my ordered pairs, if we need them. Okay,
So
go ahead.
if I didn't the original, not the
Into the original, yeah, this is the f row, right? So that's just right there, okay? Okay, so now I want to know, what if I want to know all the places where this function is increasing? What could I do? Think about the behavior of the derivative for a second. Where are the only places where the derivative has a 0 value? 0 and 1, okay? The derivative function is defined everywhere. It's a polynomial, right? Okay. So what can you tell me about the behavior of the derivative for values of x less than 0? Tell me something important about it. Say it again.
Negative positive.
Well, I guess we could see. How would you know? could we know? Before we even find out what this, what the sign of the derivative is, and that's where we're going with this. Is there any possibility that the sign is going to change over here? How come?
There's no zero.
Because there's no zero, right? Is everybody getting this? There's no zero, and we found all the critical numbers. We found every place on this function where the derivative has a zero value. There are exactly two. The derivative is a continuous function, right? So there's no way for it to change signs except by passing through a zero value. Agreed? So would you agree to this statement then? The derivative, the sign of the derivative for values of x less than 0 is going to be the same. It's not going to change. Whatever it is at, for example, -10, it is also going to be at -1 trillion. Guaranteed. Everybody agree with that? That's important. Give me a thumbs up, thumbs down, thumbs sideways on that. Okay. Let's hit that one again. Think about what the shape of this curve would be, right? We know that these are the only two possible places, well, these are the only two places where the derivative has a value of 0, right? So let's think about what could be happening there. If I were to sketch this thing, all I know for certain is that we're going to get a horizontal tangent here. In fact, let's go ahead and we'll make orange our kind of our little icon down here. So we know that we're going to get a horizontal tangent there and a horizontal tangent there. Guaranteed, because that's what a zero slope means, right? That's set in stone. We know that's a calculus concept that we've dealt with in the past. What could the function do around those horizontal tangents? Well, if I were to sketch this thing, and here's my horizontal tangent there, and here's my horizontal tangent there, there's a number of things that could happen. It could be doing this, right? Or it could be doing this. We're out of colors here, but could be doing something like that. Or it could be doing something like this. Or it could be doing something like this. That's it though. There's only 4. I mean, I don't know if the shape is right. Maybe it comes down here and goes like that. But you get the idea. In terms of the increasing, decreasing nature of the function, it's got to be one of those 4 things. There's no other possibility, right? Everybody agree? But so let's just say that it's purple. If it's purple, if the purple one is correct, then the slope would be what? Every place to the left of this, it would have to have what sign? Negative, because we're going in the positive x direction. The ant is walking downhill, right? If it's green, every place to the left, it's also going to be negative. If it's blue, it's going to be positive, and if it's white, it's going to be positive also. Okay? How come it couldn't change? How come it couldn't change?
No other zero.
You might be thinking, why couldn't it do, whoops, went too far. You might be thinking, why couldn't I do this? Why couldn't I just go, okay, it's gonna go up like this, but then, it's gonna go negative again over there.
Because there has to be a zero.
There would have to be a 0 there, right? And there isn't. So it can't do that. It has to be consistent behavior over here. It has to be the same everywhere, or we would have had another critical number, right? What if the derivative wasn't continuous? And this one is continuous. It's smooth, right? It's a polynomial. What if it wasn't? Or what if the function wasn't even, right? Then that would still be true. Maybe that, that's going to be, I don't want to go there right now. I'll do another example. I think that's going to confuse things. Let's just keep this as simple as we can for this first one. Okay, so how could we know what is the sign of the derivative for values less than 0? It's the same everywhere. So what do we do? What do you think? Suggestions?
We find the secant line with 2 negative numbers.
Well, you could, but we don't have to be that complicated. Any point. Pick a test point. Exactly. Pick a convenient test point. Because it doesn't matter what the value is. All we care about is What's the sign of the derivative? We just need to know what goes there, what that sign is. So what's a convenient point to pick?
-1.
-1, why not? Let's pick -1 as our test point. If we pick -1, and we throw that into our derivative function, and while we're at it, let's throw it into the factored form, right? That's the easiest way to determine a sign, because then all we have to do is take the product of the signs of the two factors. When x is -1, what's the sign of that factor right there? Okay, good, so I'm gonna do it this way. F prime of -1 equals negative times, what about -1 there?
Negative.
What's negative times negative? Positive. Everybody agree? Okay, so we can say something then. This tells us that this interval over here is an increasing interval for the function, guaranteed, right? Does that make sense? So we're able to say, we can make the statement that f of x is increasing on the interval where x is less than 0. Every place, right? Because the derivative is positive.
How would that look?
Well, it could look like lots of things. So it could look like this, right? So let's just say that this is that tangent line at x equals 0. It could look like that, possibly. Or it might look like this. We don't know that yet, right? There's lots of things it could be. I mean, really, those are the two main possibilities. Yes?
If it's going from 6 to 0, isn't it decreasing?
Say it again.
If it's going from a positive to 0, isn't it decreasing?
From positive, no, because, see, this is, now what you're thinking is, you're thinking of this row,
Yeah.
right? See what I'm saying? Okay, we're looking at this row right here, and you gotta kind of just think in terms of, I mean, it's a brain twister as you get used to this. But this row is referring to the behavior of the derivative, right? So this is telling us the sign of the slope of the function, and it's positive. So it has to be walking uphill on this entire interval. Lauren, that's a good question about what does this thing look like? And right now, we don't have the tools to distinguish between these two things, but we will soon. Because we're going to be able to identify, if it were the purple case, as opposed to the green case. If it were the green case, there would be another interesting point there called a point of inflection where we change concavity. And we'll be able to find those within a week, okay? But for now, we can't, all right? Okay, let's keep going with this. How do we know what the behavior of the function is between 0 and 1? Choose a test point. So what's probably our test point there? 1/2. Okay, so we're going to run out of colors for sure here. So we'll go 1/2. What is the value of what's the sign of the derivative at 1/2? So I'm going to get positive times negative is negative. Okay, so that becomes negative. So what does that tell us about the behavior of the function on the interval between 0 and 1? It's decreasing, right? Okay, everybody buy that? Okay, so then we can make the statement f of x is decreasing on the open interval between 0 and 1. Notice that I did not include 0. Is it increasing or decreasing at 0? No, it's not. Okay, so now what about this other interval for values of x greater than 1? Pick a test point. Might as well pick 2. But I could pick any test point. In fact, just to prove a point here, I'm going to pick the test point. Can we see that very well? I guess we can. I'm just going to pick the point 10, so it's really obvious. Doesn't matter which one I pick. If I plug in 10, that is positive times positive is positive, right? So this tells me then that f of x is increasing on the open interval from 1 to infinity when x is greater than 1. Okay, so that tells us a lot of stuff. Now, we get something really cool out of this that we probably didn't even anticipate. What does this have to be? If this is a point where we have a zero slope, so a horizontal tangent, and it's a point where the ant is transitioning from increasing to decreasing behavior, what does that have to be? It has to be a smooth peak, doesn't it, right? So we can say that we know this is a relative maximum. Isn't that cool? That's called the first derivative test, okay? What about right here? This is a point where we've got a horizontal tangent and we're transitioning from negative to positive, so we're decreasing to increasing. What does that have to be? It has to be a minimum, doesn't it? Because we're going from decreasing to increasing behavior smoothly. Yes, sir?
If you do look at our sideways ordered pairs with the critical numbers, can't you see that in between them it's a negative slope anyway because you go from 0 to -1?
Yeah. Yeah, you could. You're right.
Wait, then couldn't it be, sharp?
It can't be. How come it can't be a sharp one?
It's
Wait,
not
it's
the
not
critical
undefined.
Okay, because the derivative is not undefined. The derivative is equal to 0. So it's got a horizontal tangent. If it were a sharp peak, there wouldn't be a tangent line there, right? The derivative would be undefined. Okay, yes?
Is that,
That's
No,
not-
go ahead, ask your question.
how is, like, the two, like, the maximum and minimum, how are they connected?
How are they connected? So let's make a sketch. That's
That's
kind of
not
the
on the
next,
scale.
that's kind of the next step is, what if we just do a little sketch of this? Now, the sketches get a lot better when we add a few more tools to this. For right now, they're pretty rough. And remember, they're sketches. They're not intended to be graphs. They're just telling us some key things about the graph. And really, one of the key points that we want to find, and we'll see this when we do our optimization problems here coming up. You know, that's the next big kind of application of differential calculus. A lot of times, we're trying to find minima and maxima, right? And so we found it, right? That's really what the first derivative test does for us, is it locates minima and maxima, okay? So if we do a little sketch of this, whoops, let's see. So let's just capture all this stuff right here. I don't want those two.
Mm.
There we go.
Oh.
So there's all our stuff, right? So if we want to do a sketch of this, what's the sketch going to look like? Now, what's so cool about this is, this, do you see that because we put this, we ran our table sideways like this is the x-axis on our sketch, right? So all we have to do then is just kind of work our way down vertically to get the points. And if you're careful about this, so, you know, these points are somewhat proportional, you get a fairly good looking sketch, right? So here's the x-axis. Oops, that's not the x-axis. This is the x-axis, right there. So this is 0, right? So that's going to be the y-axis. And let's just locate these points. Well, one point is going to be at 0, 0, so it's right there. And one point is at 1, -1/2. So that's about, you know, right there-ish, right? And what does this thing have to look like? Well, if we're going to get a peak here and a valley there, isn't it just doing something like that? Maybe. You know, we don't know what the end behavior is yet, but we'll get there. We'll add the end behavior soon. Okay? Just so you can see, this table, I'm particularly proud of this whole table thing, because you can, when you get to do the tables pretty well, you can do so much stuff with these things. You'll get to the point where you can see vertical asymptotes, horizontal asymptotes, slant asymptotes. You can see concavities. You can see everything just all contained in that table. So it's a great way to summarize everything in a function. Yeah.
Would there be any point to using our test points and finding the y-coordinate then to help
Okay, so
polish the graph?
I would say no. I would say no, and I would say that sometimes A weaker approach to this, in my opinion, is to pick test points, use the first two rows and pick test points. And sometimes, you know, that's, people sometimes do that, and it's not very strong, because then you're having to do more calculations. It's always better, if you work further down in the table, you can work in terms of signs instead of values. And that's more descriptive and it takes less work. See what I'm saying? Okay. All right, so let's do another one. Oh, but real quick, so here's a summary of what we do. That's pretty big. Let's make that one smaller. Here's a summary of what we just did, right? So here's the first derivative test, right? And this is all we talked about. If the derivative changes from negative to positive at C, then it's a relative minimum, right? If it changes from positive to negative, then it's a relative maximum. If it's positive on both sides or negative on both sides, then it's neither, right? Okay, something that we added though that's additional to this is that based on the type of critical number it is, we can even tell what kind of a minimum it is or maximum. Is it a smooth or a jagged, right? Is it a sharp peak or sharp valley, or is it a smooth peak or smooth valley? Okay, let's try another one. Just get a little practice with this and you'll see what I mean. So let's do how about, oh, here's a good one. Yeah, that's a good one. Yeah, I remember that. Yeah, I want to do two. Let's do a really easy one. Let's do f of x equals x cubed. What's the domain of that? Natural domain. Negative infinity to
Is
positive.
the natural domain ever going to be different?
Sometimes, but not often. Usually it's going to be that. So what's our derivative? Okay, so if we make our, we can just find the critical numbers on this one. We don't have to write them down, right? It's going to be pretty easy. So x, f prime. So what is the only critical number? 0. Okay, so at x equals 0, what's the value of the first derivative? 0. Okay. What's the value of the function?
0.
Okay. So what's a good test point? Just pick one.
1.
1. Okay. At 1, what's the sign of the derivative? At negative 1, what's the sign of the derivative? Positive. Okay. So what's that mean? This function is, f is increasing on what interval or intervals?
Negative infinity.
0 to positive.
Ah, okay. Oops, not in. Oh, no, that's over. There we go. Can't remember, is that? That's and. I gotta do
I
the
thought
other
it
one.
was the U.
Yeah, I gotta go this. And, or you can use a union sign, either one. This is just logical or. Right? Does that make sense? Yes.
Does it matter if we put f or graph of x?
Oh, it doesn't matter. Doesn't matter. Yeah. Either one. So the function is increasing everywhere except 0. Okay, what do we know about, so this is a horizontal tangent, right? So what do we know that this thing has to look like then? Yeah, it's, you know that it's going to be, we call this an inflection point. So it's going to go like that, right? And that's what our graph, you know what this looks like, it's a x cubed. That's what it looks like. It goes, you know, x cubed just goes down like so, right? Okay, no biggie. So this one, I guess you could say it failed the first derivative test. I mean, I don't know if it really failed, but it didn't produce either a minimum or a maximum. Right? It told us instead that this was an inflection point. Okay? How about this one? You get one more in. Yeah, they're gonna say, they're gonna give you a function and they're gonna say things like, find the intervals on which a function is increasing and decreasing, find all relative extrema, stuff like that, okay? Yeah, here's an example. Find the open intervals on which the algebraic function is increasing or decreasing and locate all relative extremas. So you can get everything from the table, okay? All right, so how about this guy? What's our derivative this time? 2/3 times tan to the
Negative 1/3.
-1/3
times 2x.
times 2x, good. So if we want to write that in fractional form, then that's just going to give me, what, 4x over 3 times the cube root of x squared minus 4. Okay, agreed? Okay, what's our domain of this function? Okay, good, it's negative infinity to positive infinity. How come, do we have to worry about having a negative value inside this?
It's an odd.
Okay, good, it's an odd root, so we're okay, right? Right, so there's no restrictions. Okay, if that were a square root, I'd have to be careful, because then everything inside would have to be non-negative, right? So for example, the value x equals 0 wouldn't work, because I'd get a -4 inside the radical, right? Think what this means. If I wrote this in radical form, it's written as a rational exponent now, but if I wrote that in radical form, it would be the cube root of x squared minus 4 squared, right? Because the 2 on the top goes there, and this is just the index of the radical, right? And so because it's a cube root, we're fine. But if that were like 3/2 power instead of 2/3, then we'd have to be careful with this, because everything inside the radical would have to be greater than or equal to 0. We'd have to solve for x and find out what the domain is. Okay, but we don't have to deal with that here. Okay, we'll do one like that, just not today. We don't have time to do it today. So this is what we end up with. Now, what about our first derivative? Let's look at that. What are the critical numbers? We got to be careful with this one. So, are there any places where the derivative is going to be undefined?
2.
Okay, where the bottom is 0, right? It's undefined where the bottom is 0. Now, what's the most specific we can be on the bottom? The bottom is going to be 0 when what is 0?
2.
X squared minus 4, right? Everybody agree? So we could make a bubble here, and we could say that we know that f prime is undefined. When the bubble equals 0, right? Well, what's the bubble? X squared minus 4, right? So then if I solve that, what do I get? I get x squared equals 4, so x equals plus or minus 2. So those are going to be critical numbers of the undefined type. Where does the derivative equal 0? So that's one type. F equals 0, f prime equals 0, when what? When the top is 0, yeah. And when's the top 0?
When x is 0.
When x is 0. Okay, so now we can make our table, right? And we get critical numbers at 0, -2, +2. Okay, we can summarize the behavior of the derivative down here by saying that we get a 0 derivative, right? We get an undefined derivative and an undefined derivative. So that tells us important stuff. That tells us here that we're going to get a horizontal tangent line, but not there and there. Those are going to be sharp corners, right? Because the derivative, and how do we know that there are not gonna be breaks in the function?
It's not a
If we look
piecewise
at the
function.
original function, yeah, the function doesn't have breaks, does it? Right? The function, would you agree that's gonna be continuous?
Yes.
Okay, so if the function is continuous and the first derivative is not, then that tells us that those have to be sharp corners, doesn't it? Right? Does that make sense? Okay? So now let's pick some test points. That's the next step, isn't it? So pick test points.
1 and -1.
1 and -1. Let's try those. So if we look up here at our derivative, when it's written in factored form, it's easy for us to calculate. Boy, I wish I just had more. This thing used to be, what'd that do?
Glitch.
I must have made that like 0 width or something. I don't know.
I think,
Started
no, I
all the
think
colors,
yeah.
wasn't it?
you were dragging the color onto the board.
Oh, I got you.
Yeah.
Okay, so so now if we calculate f prime of 1, what's that gonna be? If I plug 1 in, what's the sign of the top gonna be?
Negative.
Positive. What's the sign of the bottom gonna be?
Negative.
Negative, right? So I'm gonna get positive over negative equals negative. So at positive 1, we get a negative first derivative. What about at negative 1? The top is negative, bottom is negative, right? Negative over negative gives me positive. Okay, another test point.
-3.
-3. So f prime of -3 is gonna give me
Negative.
negative over
Positive.
positive. So negative. Another one, 3, how about? F prime of 3, oh my gosh. Okay, so that's gonna give us positive, isn't it? Right? Okay, we'll pick this up tomorrow. So negative, but you're getting the idea, okay?